Today we are going to finish chapter 8 and start chapter 9. We have about 5 slides to finish chapter 8. It's a small section I just want to go over real quick before we move on to chapter 9. In the meantime, the next chapter, chapter 10, will be our last chapter. This will be on cases. I will make the PowerPoint slides available. Please read, continue reading chapter 10 as well. Before we get started with the last section of chapter 8, there was one question I promised to check and get back with you on that, and this had to do with finding the number of total valence electron there was a polyatomic ion, which when we tried to find the number of total valence electrons, none of them was in the multiple choice. So I want to just go back to that and look at what was supposed to be the correct answer. Let me just get back to that question and we will look at it. I think this was the question. You recall, none of the multiple choice here support our final total number of valence electron, which was 15 when we did paste on the periodic table and the group numbers. It turns out that, look at my whiteboard, that the correct ionic or polyatomic ion in question was supposed to be I, C, L, and then subscript of 4 with a negative. When we did last time, we ended up with 15 because of group 7. Group 7 is 14 plus 1 for an overall charge of negative 1 give us 15, but they should have been a subscript 4. In this case, 7 times 4, all right, plus 7 plus 1, which is 36. The correct answer was supposed to be C. I went and checked from the question bank. This is where I got the question. I like it right here on the screen. This is the polyatomic ion ICL with a subscript, and the correct answer is 36. This to bring to your attention what was supposed to or what was missing in this question. So put a subscript 4 here, and the correct answer is C. This is last week, this past Tuesday question on learning check. And basically it's just using the periodic table. Given the other elements, you should be able to, of course, find the total number of valence electron. The first step in drawing the Lewis structure for a molecule or polyatomic ion. So this is where I stopped last time. The strength of I wanted to start 8.8, but we ran out of time. It was exactly 12:30, but I want to pick up from here today. And section 8.8 is looking at the strength of covalent bonds. And remember, covalent bonds, we have 3 types of covalent bonds. All right, there is the double bond, triple bond, and single bond. Without necessarily memorizing the numbers given here, it turns out that this is the weakest, all right, in terms of comparing the 3, and this is the uh, 'strongest. 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 'strong and then the double bond is in the middle. It's just like if you are given 3 sticks and you are asked to break, of course you will need a lot of energy to break the 3 sticks. But if you have one, you will use less energy to break. So when you look at the double bond, triple bond, this is how you look at it. Now, uh, what is happening in terms of, when you look at these values compared to which trend are you going to use? I've given you the double bond that it is easier, but here the trick is using electronegativity values, using electronegativity values or the trend on electronegativity on the periodic table. This is how I look at it. If you think of atomic radius, the trend on atomic radius, this is what we looked in chapter 7. It decreases as you go from, it increases as you go down a what? Down a group. And it increases as you go, and also the electronegativity. Electronegativity plays a role in terms of if there is equal sharing of electron, then the displacement of electron will not be confined to one atom. Let's see, if you see this, the first element is carbon. All of these they are single bond. These are group 7. Let's see group 7 here: chlorine, bromine, and iodine. If I have carbon here, I may have used a different color here. Let's assume that I'm able to maintain the radius of carbon atom, carbon atom, carbon atom. What happened when you go down a group? The atomic radius increase. That's what we learned earlier on. So let me use a different color coding to now have fluorine, which is a little bit smaller than carbon, but chlorine is a little bit bigger, and this one is even bigger. So I have here fluorine, all right? I have here chlorine, I have here bromine, and maybe here there is carbon. There is carbon, and of course this will be big. This one will be the biggest, iodine. So if you use this, have this in mind that this atomic radius for carbon is constant, it's not changing as you go down. I'm looking at these compounds. They all have a single bond, but the atomic radius for anion keeps increasing as you go down the group. If I make a connection, all right, if I make a connection, let's say this one, if you look at what is happening, it is increasing as I go down the group. I'll use this to say that if you have a small, all right, if you have a small piece of stick, it's so hard to break. But as it gets bigger and bigger, you will have greater leverage to break that stick. All right. So the longer it is, the easier it is to break, which explain the trend in, all right, the trend in the energy that the smaller it is, you will use more energy compared to when it is long. So the trend, it is decreasing as you go down the group. The strength keeps on decreasing. Now, if you use this approach, reconciling the trend in atomic radius all right, you will see the pattern in which the bond strength changes given the constant element, whereas the cations keeps on changing. So it has to do with how the atomic radius changes based on what we were given earlier. I don't want you to memorize this and say, all right, maybe 276 for carbon bromine and this. The question here is about just a general trend that when you are given this, how is it changing? How is it changing as you go down the group? If you look at this bromine, this one also is, we go down the group, it keeps on increasing, and you see the trend is following the same pattern, So bond strength, and recall the units here, kilojoules per mole. That means if we have 1 mole of nitrogen, hydrogen, that's how much we'll use bond averages. So from this table, that is one I want you to take home and use that approach in arranging either the elements according to the increase in bond strength or decrease in bond strength, or if you are asked which one of the following will have the strongest or the weakest. I think I did mention this for multiple bonds, all right? Multiple bonds right here. This is the weakest, this is the strongest. If you look at this carbon, triple bond versus what? Versus double bond, 614, 839, and I think in the previous section we have carbon, you see 348 versus 614 versus 839. I don't need you to memorize the numerical values, but if you look at, let's maybe for other questions, but the general trend here is always the single bond is the weakest and the strongest is the uh, triple bond. It's the triple bond. That's what I want you to know in terms of bond strength. All right. Let's see. If you look at just a typical question you'll see in the exam, you don't need to memorize the numbers, but given a table similar to what you see here, this is the change in energy required to break the the single bond between carbon, double bond, carbon, hydrogen, chlorine, and so forth. You are given here. The question is, using the table for bond dissociation energies, the change in envelope for the following gas phase reaction in kilojoules. So the equation used here is you need to find out the number of bonds formed minus the forms broken to calculate. You need to find the number of bonds formed in order to form this product minus reagent. So I look at how many carbon. It is what? 1, 2, 3, 4. You have 1, 2, 3, 4. That is the number of, so if I have here, let's see, 4, here is hydrogen or carbon, which means 4 times what? 4 times 413, gonna give you the value given there. This is 1, 2, 3, 4. And then carbon is 1. So 1, this is carbon. So 1 times 614. I don't see any other bond in this compound. And then a hydrogen chlorine is what? This is 430. So hydrogen chlorine. This is 1 times 431 equals to, and then this is for the product. What we need to do is now, this is 614. You're gonna add all these 614. This is for that one. That is 12, 5, 16, 16, 32. And then we need to find for the product, somebody to do this calculation for us. For the product, we have hydrogen carbon. Let's say carbon, hydrogen. How many do we have? 1, 2, 3, 4, 5. I see 5. I'm looking at this hydrogen carbon. 1, 2, 3, 4, 5. So this is 5, which is 5 times 413. It's gonna give you some value there. And then there is carbon, 1 carbon to carbon, which is this. You see, I'm looking at this. Carbon is 348 times 348 kilojoules. Now, here there is carbon chlorine. This is carbon chlorine, which is 1. This is carbon chlorine, which is 1 times carbon chlorine is 328. 328. Somebody do for us this calculation. How do we take it from here? What is the equation used to calculate the change in envelope? I think we learned this before. It is the product minus change in envelope using the formation. The product reagent, you have to look at where the products are. All right. It's gonna be the product. So this one is 5, 15, 6, 20. This is 348, and then this is 20. What is 320? 328. So you need to add the total energy for the product minus reagent for point dissociation energies, which is the same as for product. In this case, you say product minus reagent delta change in dissociation energy. It is given from reagents, all right, minus product. All right, minus product. So in other words, what is the value? Everybody, let's go this. What did you get for this value? Let's see this. What did you get for this value? I'm looking at this. Look at my whiteboard. Somebody say negative 44. Thank you. Somebody, Leila, got 44. Alexandria, 44. Somebody did the product. So remember, I don't have my calculator with me. If you look at what I did is I had to look at the bonds. This has to do with the bond strength. The point here is once you know how many bonds you have, and I'm gonna give you, structural formula, all right? Because if I give you something like this, somebody might get confused. C2, H what? H4. All right, you see that? It's the same, this structure is the same as this, except that this is condensed. This is condensed structure here. If it is in this format, you may not be in a position to really see where the double bond is, where the single bonds are, and what is connected to that. But I think it will be helpful if you have in this form, the way you see on the PowerPoint slide, you will see the double bond, you will see the single bond, and you will be given a table similar to this. All you have to do is do the math that how many of hydrogen carbon do I have, how many carbon in that way, and then you do the math for the reagent. Look at the arrow. These are the reagents. This is the product. If we add another product on this side, we will have to sum everything for the product, sum everything for the reagent, and then we plug it in this equation right here. It is the change in bond dissociation energies for the reagents minus for the product, and of course negative means exothermic. The other uses negative to means it is given off. So the correct answer for this is A, is A. Other than that, that is all what I wanted to bring to your attention. The bond strength, we looked at that, double bond, triple bond, which is being reinforced in this slide, that a lot of energy for triple bond compared to double bond, compared to single bond. And of course, the bond length. That bond length, that single bond is always longer than triple bond. This is the shortest. You see on the x-axis is the bond length in angstrom. And of course, 1 angstrom something we looked at in measurement. So I will make the assignment available and the quiz for chapter 8. Please be on the lookout for the quiz, which will be available not later than tomorrow. Here is a learning check question. Which bond has the highest bond dissociation energy? That means it will need a lot of energy to dissociate. Of course, it is C. Probably in the exam, I'll ask you which one will have the lowest. If you look at the single, but both have single. This one is shorter compared to that. So if it's the least, this is this correct answer. The highest bond dissociation, you will need a lot of energy for double bond, for triple bond, sorry, triple bond. Please do the homework assignment. I know it's probably maybe due sometime next week. I will, as we approach the end of the semester, I will try, synchronize my gradebook on MyLab and mastering onto Canva so that you can see the total at the end, the average. Probably right now, what you see on gradebook, on Canvas, does not account or take into consideration the grades from homework assignment on MyLab and mastering. And I want when we take the final exam, you will have an idea of where you stand, all right? Please do the homework on time, use to practice for the coming exam. Any question before we move on to chapter 9? So remember the quiz will be available, and I did post announcement about the SI times. Please make use of those resources available for you. Now, let me X this and then load chapter 9. All right. Chapter 9 is the same as, it's just continuation of chapter 8, basically. It's continuation of chapter 8. I've thought using different text, and some other stages have 8 and 9 as one chapter. And in 9, all right, let's see. In chapter 9, what we will look at is the molecular geometry, and why do we need to learn the molecular geometry of molecules? When we say molecular, it's not ionic compounds, it's a molecular geometry. It turns out that whatever we have been looking at in chapter 8 was, in terms of Lewis structure for molecule, was oversimplified. All what we looked at in chapter 8 was the number of atoms and the connection, the type of bond, but we did not look at what? At the molecular geometry. I had one of my, I know some of you may have used the molecular models, all right? I had my own model here. I brought with me. Oh, it did drop. I wanted to show you what we mean by molecular geometry. When you draw the Lewis structure for H2O, give you what we mean by molecular geometry. H2O, you may end up with this structure here, and then you put the D dots there, all right? You may even change the single bonds here to dots, doesn't really matter. But you will see in the text, all right, I don't know if you can see this. This is in modeling, molecular model, this is considered as hydrogen. The white sphere here, this is the single bond. Of course, this is carbon right here, all right? This is carbon right here, and this bond. If you look at this, this is the actual shape of water molecule with the two pairs of electron assuming that position. That is the objective of chapter 9. That is the objective of chapter 9, to look at the molecular geometries and bonding theories. Somebody let me just answer the question here, or the question was answered. Somebody is saying, asking question, Trinity, you had a question. I guess I will look at, let's see, what was the question? Jason, you had a question?
Yeah, so I'll just give you a breakdown. I asked, are the dynamic study modules for any type of grade, or is that just for extra practice? And then Trinity asked if the exam was on Tuesday or Thursday, and to clarify what the exam would cover up to.
Okay, I'll even if I not cover chapter 9, and then I will set the exam to cover up to wherever we will cover today. And if you feel that Tuesday is not enough, let me know. This is your exam, all right? I don't want to rush you. Now, as far as you are asking about, the dynamic study modules, let me just really quick share with you how they create look like, or how I will calculate the overall grade. I don't want you to miss any of the all right, any of the points from different categories. How I will apart from, all right. Jason, here is the dynamic study modules, and you are asking if it is part of the grade. Yes, out of the 5 which they are due at the end of the semester, all right, they are always available. You have to do 5 of those, and I think 5 are available. That will be average to uh, 8 points towards the final grade. There was a Canvas check assignment I gave you at the beginning of the semester that you understood everything. Please also take into account that 2 points from that exercise will count towards the final grade. Of course, the quizzes, this is what I was saying, I will have to put from the MyLab and Mastering on the Blackboard so that you see where you are, quizzes, midterm exam, and the final.
So the only dynamic study module I have, except for, so they have like 4, which is like nomenclature, element names, key math skills ones, and then a chapter 7 one. I'm
Okay.
just supposed to do those 5.
Oh yes, 5. If not 5, I'll look at it into that. If not, maybe you cannot see from your end. I'll look, but they will be.
Chapter 7's the only like chapter specific one we have.
You only have 7?
Yeah, so I have like basic ones that are like key math skills dynamic study modules, and then I have a single one for chapter 7. I don't have one for like chapters 1 through 6 or chapters 8, 9, or 10. I just have chapter 7 and then like significant figures study module.
Yeah, it's not all of them, because if you look at 5 of them, it will reconcile with not the entire chapter. If we were to do dynamic study modules for each chapter, and then I'll have assigned new 10 of them. So not necessarily that to reconcile with each of the chapter or question from each chapter, but only 5 dynamic study module, not necessarily covering the entire chapter or covering the entire chapters we covered by the end of the semester.
Wait, so Carolina just said she has up to chapter 24. Okay, cool. Okay,
Yeah.
Lauren just cleared it up. I just wanted to make sure I wasn't like missing something, but I understand, I think.
Yes, you are not missing anything. You are not missing anything. So if you look at 5, you'll be like, if I'm doing chapter 1, 2, 3, 4, 5, what about 6, 7, 8, and 9, 10, right? And if I want to, somebody say they have 24, they are going to the global. I could be wrong. I'll check that. Somebody is going into the global mastering. You have to go through Canvas in order to look at what has been assigned. All right, what has been assigned. So if I go to assignment, I don't know where, if you go to my mastering, and you will see a lot of more than that. Let's see if I have 5. If you look at this, 1, 2, 3, 4, 5. Jason, can you see those 5?
Yeah, I just didn't like, so they're not chapter specific, so I was wondering like if there were other chapter specific ones. So Carolina said she can access the rest of them. How do I get to where I can do DSMs for the, like if I wanted extra practice on chapters 8 and 9, is there a place I can get that?
Okay, I see what you mean. If you want to practice something extra, right?
Perfect.
I will paste on your request and somebody else. I'll make that available also, the rest, so that you do not, you can practice on it, but it will not affect your assigned dynamic study modules. If you look at chapter 1, practice, this one will not work as homework. And you see, this is homework, right? Chapter 1 homework, and then there is chapter 2 practice. So likewise for these dynamic study modules, even if I make it available, know that these are the only one which will count towards your final grade.
Gotcha. Thank you.
Yeah. So if I make that, even if you see like dynamic study module number 8 down here, and then it will not count, all right? I'll make that, all of them 1 through or whatever it's available, but this is what you need to pay attention to.
I think they're already available. So Lauren said in the top right corner, there's a button where you can actually go to all the dynamic study modules.
Yes,
So
you can do that.
perfect.
You can do that. That will work. Thank you. Any other question?
You said that the exam last time that we were in class, you said that it would just cover up until 8.8, and then just now you said that it would cover through what we do today. So is that changing or?
Oh, 8 point, let's see, 8 point, what we covered 8.8, which is covered today, 8.8.
Yeah, last class you just said that it would
Whatever we covered last time,
study. Yeah.
which was 8 point what, 8.7, correct?
Yes. I just want to make sure if the exam is going through 8.7 or if it's going through the stuff that we do today too.
8.7 based on 1 week time duration. I always keep for for any major exam, you will have 1 week, but for quiz, it will for quiz number 8, it will just be quiz number 8, quiz number 9, and quiz number 10.
Right. Okay. I just want to make sure because I thought you said at the beginning of this class that it was
No, it's the quiz.
So.
Okay,
gotcha. Thank
you. And normally when we cover this, because of the time constraint, we don't. For chapter 10, you may only have to take the quiz without seeing questions on chapter 10. Let's not even get there before we get to 10. Let me not jump chapter 9. All right.
So just to clarify, only chapters like 6 through 8 will be on this exam that we're taking on Tuesday.
Not all of 8, up to 8.7.
Okay.
Yep. And as always, let me even make the make live issue. I will send out the study guide similar to what I've been sending. You know, always I send out like you need to read this, and of course, you will not see chapter 9 on that. I will save that for you will cover in the quizzes what you will see in the final exam for 9 and 10. Okay. Any other question? So if there is no question, please check your UNF email account by end of the day on what you expect on the upcoming exam, which will be from what we covered last exam to 8. Let me just note that 8.7. But for the quizzes, I will make 8, chapter 8 quiz, chapter 9, and chapter 10. So chapter 9 is on molecular models. As I said, in chapter 8, we only learn on Lewis structure of molecule, and what Lewis structures of molecule tell us is only the number of atoms and the connection, the type of bonds between them, but doesn't tell us the molecular geometry, how molecules look like. I'm molding a sample or a model of water molecule, and for my whiteboard, this is the actual or the molecular shape of H2O. This is the business, or what we'll be learning in chapter 8 is how do we end up with this? We will use a powerful model we call Fallon shell electron pair repulsion model, which is used to predict the molecular shape of molecules. So when you see here, you're not going to be dealing with ionic compound. This is the roadmap of what I intend to cover in chapter 9. The molecular shapes. This is the model used to predict the molecular shape. And the reason why we are interested in shape is that the shape of the molecule affect the physical properties and chemical properties of a molecule, right? Why do this molecule dissolve in this substance and so forth? Why this molecule react the same way as this? is because of the molecular geometry. 9.2, we look at the valence shell. This is stand for, you may see this. This is stand for valence. And then S is for shell. All right, this is valence shell. E, valence shell. E here is for what? Electron, valence shell, electron. P for pair, all right? And then R is for repulsion. Why? Repulsion, electrons are negatively charged and they tend to repel each other. That's where the term or this repulsion in phi SEPR stand for. In 9.3, I'll show you how you can predict molecular geometry of a molecule from the Lewis structure for that molecule pi. Now you should be able to draw the Lewis structure for molecule or an atom. In chapter 9 also, we will look at the bonding theory. You know, when we say theory, it's like something we have to in theory, but not in reality. For example, in this water molecule, which electrons are responsible for forming this bond? We will look at how the valence shell, valence bonding theory and the molecular bonding theory and hybridization. We look at the multiple bonds and lastly see the molecular orbitals, not the atomic orbitals. I know we look at atomic orbitals when we are writing the electron configuration of elements. Now, molecular shapes. What determines the shape of the molecule is the bonding, the bond angle. Molecular shape, when we talk about the shape or angle, this is where we are talking about the bond angle. And at the outset, from the Lewis structure, we know they are bonding and lone pairs. These are the bonding electron, bonding electrons, and these are the lone what? Lone pairs of lone pair. This is another lone pair of electron. You know how to classify electron. And I want, when we look at the shapes right here, when we look at the molecular shape, to predict a molecular shape, it is based on the central atom. All of them are based on, unless it is linear, of course, such as organic molecules, the shapes are based on the central atom, which I've used the yellow box right there to show you how we talk about the shape. We use the Lewis structure, of course. You see this? By now, I know you know how to write or draw the Lewis structure. If you don't know how to do it, and then molecular shape will be a challenge to you. Now, the examples given here, these are just molecular samples of molecular geometries, molecular shape of compound. This is carbon dioxide, sulfur dioxide, sulfur trioxide, all right? If you look at these terms here, linear, pen, trigonal planar, trigonal pyramidal T-shape, these are the terminologies used in making or describing the molecular shape. Let's see this. I don't want you to look at this. I want to explain what this AP2 or AP2, AP3, 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 and say every time I look at this, and then I know it is AP3. This is the general formula, all right? Predicting molecular shape, all right? This is the general formula. A, P, X, and then E, and like that. Let me break down this. Let me break down this to form. Let me break down this to mean A. This is central atom. B, X. We call this external atoms. Number, let me just put that number of external atoms, how many they are. For example, here we have two external atoms. A is for the carbon you see here. P2 means two external atoms hooked up to what? Hooked up to the central. You may think that why this one is AP2 and this one is AP2. We talk about linear, we talk about pen. It has to do with this EN now. EN, these are number of lone pairs on central atom. All right, number of lone pairs on central atom. For water molecule, if I go back to this, molecule, I can say that this is A because there is oxygen. And then P2, you see this, we have two hydrogens. We have two hydrogens hooked up to what? To the central atom. And if I look at the lone pairs, we have to, I'll say that it is E2, that there are two lone pairs. There are two lone pairs, and always these assume the shape of the, we will come back to this. Don't worry about, the pen. I was just explaining to you. Look, I was explaining to you what these terms stand for and how you will use these down the line, okay? So likewise for AP3 means the central atom here is A and we have three external atoms. AP3, we have three and then external atom. We'll come back later on to why this is trigonopyramidal, but the point I want to bring is how do we use this? How do we use this general formula? Please remember this, APXN is what you will be using in predicting the molecular shape. That is where we are going with that. And why they assume this is based on the interaction, all right? Have that in mind. A is the central atom. B is the number of external atom bonded to the central. And this is the number of lone pairs on the central atom. Remember, molecular shape is based on the central atom. As I say, the bond length, two things determine the shape: bond length and bond angle determines the shape of what? Determine the shape of the molecule. The bond length and the bond angle determines the shape as in linear. So for linear 180 degrees, so for a linear molecule, the bond angle around the central atom is 108. For trigonal planar, tetrahedral, these are 1, 2, 3, 4, 5. These are the 5 molecular shapes you need to remember. You need to remember in describing the molecular geometry. Please learn when we say linear, how does the bond angle, how are the external atom aligned around the central atom? Trigonal planar, bond angle, tetrahedral. There is a trigonal pyramidal, and you have to see. This is called the axial, going up, axial position, equatorial position around here. And this affect that in the bond angle on the equatorial is 180, but for the axial here, 90 for octahedral. So as we move forward, these are the 1, 2, 3, 4, 5 molecular shapes we need to learn, commit to our memory, and I will show you down the line how we arrive at those shapes. We know electrons are negatively charged and therefore they tend to repel each other. Therefore, with that, the repulsion leads to what you see in terms of the shape, in terms of the bond or angle, in terms of the bond angle. This is what the meaning of phosphor VSEPR, valence, from the valence shell, valence electrons, they tend to repel. In preparation to predict a molecular geometry, we need to know what is meant by electron domain. Electron domain. An electron domain with respect to the central atom, remember what we are basing on in terms of the molecular shape is the central atom. This is external atom. This is external atom, this external atom. From this generic chemical formula, I can say it is of this type. Based on what I just explained to you, we have 3, and then we have E1. That means we have a lone pair on the central atom, assuming that this is my central atom. These are external, that's 3, and then the lone pair right here. An electron domain can be unpaired electrons. It can be a single bond, or it can be a double bond. Even triple bond can be a domain. In other words, this is a domain. This is a domain. This is a domain. Even though we have 4 electrons, we count a bond as a domain, whether it is a single bond, double bond, or triple bond. The single bond here is a domain. The unpaired electrons here, the single pair is a domain. So this has 4 domains. I can say this has 4 domains. A domain around the central atom, All right. That's what we're gonna have, that central atom, molecular A has 4 electrons. Let's see, while you are answering that question, some folks had some questions here. Lauren, of course, somebody, Jason, say 7 to 9. No, we will adjust that, Jason, we will adjust that, not 9. That is correct, 6.8. We didn't finish 9, that's fine. So I will not test you on 9 just because of the syllabi. We can adjust that based on the circumstances. So it's not 9. That is what I say. You're right, Lauren, 6 to 8.7. All right, I hope we are all on the same page. Let's look at the learning check question. In counting the electron domains around the central atom in valence shell electron pair repulsion theory, a dash is not included. Non-bonding pair of electrons, core electrons, single covalent, double covalent, triple covalent. Which one is our, what is the correct answer for this question? Based on what we just looked at in counting the domains. Use the chat window, please, and see. Yes, Alexander, you're right, correct. The correct answer is C. We do not use the core. From the definition, we use the valence electrons. Only valence electron participate in, of course, bonding, and we do not count we do not take into consideration the core electrons. Let's see how valence shell electron pair repulsion model work in terms of, shapes assuming the linear, which using two balloons, the electron domain, you see this, the point length assumed to be there, and these are the external assuming the central there. This is 3 loops pointing in different direction. Using the analogy of balloons, electron pair tend to repel in valence shell electron pair repulsion model. There are 6 models, all right? There are 6 molecular geometries which are on table 9.1. If you look at the electron domains, that means around the central atom, there are 2 domains, 3 domains, 4 domains, and 6 domains, all right? Before you predict the molecular geometry, you need to know the electron domain geometry, all right? This one does not include, on table 9.1, it does not include the lone pairs. It doesn't show you the lone pairs, but I want to give you another table, which I'll allow you to use in the exam and quiz, on how you can predict the molecular geometry. You know, the point here is, how should I predict the molecular geometry based on the domains? I don't want you to just look at, the chemical formula and say this is linear. If it is of this type, all right, if it is of this type, A, P, 2 with no lone pairs of electron on the central atom, and then this is linear. I may have a different, all right, I may have a different molecule or polyatomic ion, but the basis of coming to a conclusion as linear or trigonal planar, trigonal power parameter, or seesaw or T-shape is based on this. Based on this, it is only AP. Remember what I explained earlier on, for a linear, you see this linear, it is of this type. And there is a table here. Look on the screen. This is at the outset. All right, I'll blow up this. And I think this is also available in the, it is available online, all right? Yeah, this is available on Canvas. Please check this. This is the summary of Fallon shell electron pair repulsion models. So sorry about the, it's kind of like flood. When I Xerox, it didn't come out correct, but still you can see that the domain, this stands for the lone pairs on the central atom. Where you see 0, this stands for lone pairs. These are just examples of molecules, and these are the bond angles. You can look at the bond angle from the text. This is what you will, terms of electron, there are two. Of geometries. There are two types of geometries. There are two types of geometries. One, electron domain geometry. That means looking at, you may see that abbreviation, and then this is molecular what? Molecular geometry. Molecular geometry.
If you're writing on the whiteboard, we can only see the summary.
Oh yeah, sorry about that. Yeah, right. Let's see. I wanted to show you two types of. Before we come back to this, all right. Before we come back to that, these are the two types of geometries, which question could be specific to either this or this. And if you look in the text, we have electron domain geometry. That is looking at the electrons around the central atom. And then there is the molecular geometry. So there are two types of geometries for every. Why are we saying linear? Linear. It cannot be always the same, all right? It cannot be always the same for when you have two that, oh, I have two things connected. And sometimes even you may have something like this and like this. And somebody may just use and say, oh, everything with that two should be linear. No. You have to follow the steps. Let me write or draw the Lewis structure, which you should know. And then again, now factor in how many lone pairs of electrons do we have. I'm just gonna give you an example of H2O, all right, of H2O, which assume this shape with hydrogen there, and then there are two, all right, there are two lone pairs. If I look at the electron domains, we have four here, 4 electron domains. 4 electron domains, we have one domain here, we have one domain here, we have one domain here, we have one domain here. Electron pair, this is a domain. You may have seen somebody using this. This is a domain, that is a domain, this is a domain, this is a domain. So when we describe this, for water molecule, I will pull this right here, that if you have four electron domains, you see this? For example, H2O, we have 2 unpaired electron on the central. So we're talking about 2 domains. You look at this, 4 domains because of 2 and 2. If you look at electron domain, it is tetrahedral. So for H2O, this is electron domain is tetra what? And molecular geometry here is pent. The point I want to bring is how do you differentiate between the molecular geometry and the electron domain geometry. Electron domain geometry only look at the electron domain around the central atom, but the molecular geometry look only at the number of atoms around the central atom. Electron domain geometry and the molecular geometry. These are the type of geometries you have to pay attention to and know how to use the table. This is linear. So electron around for linear, we look at that. For trigonal planar, we'll have to look at that. If you look at this, what is the molecular geometry of CS2? If you look at these two molecules and this, somebody may say it is linear because this one was linear. This was linear, and then maybe this one also will be linear, assuming that they are looking at the PowerPoint slide and they don't know how to go about with that. You may think that they will all have linear when you have to know. That is not the case. If I were you, I will have to start from the basic. What do I mean by the basic? Drawing the Lewis structure for a given molecule or polyatomic ion, which in this case, draw one. You have to draw one. You have to draw the Lewis structure. So for this, carbon is in group 4, so it has 4 valence electrons. Sulfur is in group 6, so it has 6 times what? 6 times 2, which is 12. And then when you add that, we have 16. That's what we learned earlier on in chapter 8. This means carbon is bonded to sulfur. From 16 minus what? Minus 4, I've used 2 here, I've used 2 there, so remain 12. From the remaining 12, external atom should take first priority in fulfilling or satisfying the octet rule. I had to satisfy the octet rule in the external atom and then do the mass. Make sure the central atom, except with the exception of boron, we looked at boron last time, there are some exceptions, except hydrogen. Of course, it cannot be a central atom. So that we're gonna make a double bond on either side. To satisfy the octet rule on couple, we make a double bond on either side. So once the central atom satisfied the octet rule and you have the Lewis structure, that is now when you can come back here and say, what is, here we are talking about the molecular geometry. It is A, P, 2. I don't see any lone pair on the central atom from what I had to do, I don't see any lone pair on the central atom. So if I had, look, if I had this, gonna have this. If we had lone pair of electron, I'll use this. Look at this. I had to use this so that you can see the lone pair E1. So it is of this type AP2, and AP2, we are looking at the geometry of the atom. Geometry of the atoms, it is linear. So I'll say this is linear. If I'm looking at the electron, geometry of electron pairs, this is electron domain geometry. This column right here is electron domain geometry. This column here is the molecular geometry. Geometry of atoms is the same as, all right, geometry of atoms. Let me just, I was writing something here and want to make sure you see geometry of atoms from that table. This is the same as molecular geometry, molecular geometry. So here, molecular geometry is the same as geometry of atoms. Using this table right here, I don't want you to get confused. Geometry. And then geometry of electron pairs. Geometry of electron pairs here, all right, stand for electron domain geometry. That means you are looking at the domains around the cell, electron pairs around the cell. That means you have to account for the lone pairs. Here you only look at the atoms. You may see Mg for molecular, and then EDG for electron domain geometry. It's the same thing. So for we move forward, for this, the correct answer is linear. The correct answer is linear. From what I just did, you should see that I'm using the Lewis structure to predict that. Any question on this slide here, please? Any question? So trigonal planar, this is the same as, just using the general formula always. An example of trigonal planar, all right? You may see, let's see, for example, something like this. Let's see what this will give us. I don't know. We'll see. So if we had to draw the Lewis structure for this S equals to 6. I'm drawing the Lewis structure. Oxygen is 6 times 2. This is 12. And if I add, I have 18 valence electrons. This is stand for valence electron. I don't want somebody to say, is this a term? Maybe valence electrons, so maybe so that you understand. So this is bounded to 2 oxygens. External atom takes first priority. So I have this, I have that. I've used 12 to remain. And then of course we make a double bond using either one of the oxygens. So this is of this type. If I look at the central atom, it takes this shape A, B, 2, E, 1. This is the shape for or the generic formula for predicting either molecular geometry or electron domain. For molecular geometry, I look at oxygen and oxygen. But if it was electron domain geometry, there is one domain here, there is a domain here, there is domain. So 3 domains. 2 plus 1 is 3. Instead of just looking from here, it might not really help you out. It will not help you out. I'll just go here and look at the 3 domains, 2 with lone pairs on the central atom. 2, if I add this and this, these 3 domains, all right? And the shape is pan shape. So this will be molecular geometry. Molecular geometry. And then electron domain geometry is trigonal planar. So if I was to answer a question on trigon or on electron domain geometry, for this is trigonal planar, but for molecular geometry, it is the either fish-shape or pan. It's the same thing because it assumes this general formula: A for central atom, B for the external atom hooked to the center, and then E for the lone pairs on the central atom, So I'm just using the, sulfur or sulfur dioxide to show you how you can either answer a question on molecular geometry or electron domain geometry, and you know how it look like for trigonal planar, assuming that there is no lone pairs. So sulfur dioxide, which is what we have here, it has 2 bonding domains, which is this one domain, and there is one non-bonding domain. This is electron pair E1. The one I'm just showing you here is E1 is the lone pairs of electron. Remember the lone pairs of electron. From the general formula we looked at the very beginning right here. Remember the formula I gave you? That E stands for number of lone pairs. We have 1 lone pair. We have 2 atoms hooked up to that, and then we say it is band. So it doesn't have to be necessarily that I need to memorize, all right? That I need to memorize for nitrite. This is nitrite ion, or boron trifluoride. No, it's not going to work. Suppose tomorrow something else is presented in exam, such as the one I've used here, sulfur dioxide. Using the same approach, you can do that for subsequent geometries. So sulfur, how will this one look like? Let me just, before we move on, for sulfur, let's all look at this. Sulfur is in group 6, so 6. Fluorine is in group 7, and we have 2. So fluorine is 7 times 2. This is 14. If we add that, this is 20. No, 20. Yes, 6 plus 14 is 20. Valence electrons. So if that is bonded to fluorine, we have used 4, remain what? 16. So this what? This takes 6, this takes 6, and how many remain? So we have used 12, remain 4. It doesn't really matter if you put there or if you put there, so long as we look at 4, 4. 4 remaining, we keep it to the central atom. We don't need to make a double bond because each atom satisfies the octet rule. Now, let's narrow into our central atom. We use the central atom to predict either the molecular geometry or the electron domain geometry. And if I use the generic formula, it is A for the central atom, B is 2, and then E2, we have 2 pairs, not 4 electrons, 2 pairs of electrons around the central atom. And the molecular geometry, Mg for this, if I have the table here, look at the table. First, we have 4 domains, 2 plus 2. So it is this. Look at A, P2, E2. A, P2, E2, which means the molecular geometry is paired. So if I was to draw that, it is a band shape. And if you are to draw, it's going to assume this shape that the lone pairs, they repel each other, and then it's going to put this bone right there. But electron domain geometry is tetrahedral, tetrahedral. So that is the correct answer is pen shape. So the lone pairs will be there, fluorine will be there, fluorine will be there, and electron domain geometry, this is tetra what? Tetrahedral. And then molecular geometry, this is pen shape, pen shape. That's how I'll use that table. I'm looking for molecular geometry, which is pen shape right here. So correct answer for that is B, is B.
I have a quick question when you're working through that. How do you know not to add like a double bond and instead put the electrons on top of the central atom?
Right here, right?
Yeah. Like how do you understand to not like create a double bond between the sulfur and the fluorine, but instead add the extra valence electrons to the central atom?
Yeah, there are two ways. You can use that. One, or the sure way is making sure that each atom satisfies the octet rule. The only way we create double bond or triple bond is when the central atom needs more electrons to satisfy the octet rule. But the way it was, when I satisfied the octet rule on the external atom and put the remaining on the central atom, and then now do the maths and see if each atom satisfied the octet rule, then I don't need to make a double bond. So from here, if you look at fluorine, 1, 2, 3, 4, 8 electrons. If you look at sulfur, which is the central atom, 1, 2, 3, 4. So I know I don't need to make a double bond. If I do this, so there is no need to make a double bond where it shouldn't. That is one way of looking at it. And then of course, the other way is fluorine cannot make a double bond. It has single electron, which is available for bonding. So always you can also use the lone pairs and say, even though there are some with single or electrons around it, I don't want you to get confused with, say, carbon has single bonds around it, but the maximum it can form is 4 bonds, but it can form double bond or triple bond. So sure way of making a double bond is because of the octet rule.
Okay, thank you.
Yes. As opposed to this, let me go back to this. If you look at this, before I made, before I made a double bond on this, it was like this. It was like this. Remember that? It was like this. So when we do the math and say this one has 8, this one has 8, this one has 6, and yet we need to make 8. No, so let me make a double bond here. That was a good question, because chances are somebody might think that we always need to make that. Does that make sense? Lauren? Hello? Does that make sense?
Yes.
All right. Thank you. Selena, you're wondering what time our final, it will be just during the regular class hour, 10 to, we meet during that regular time. More information will be shared for final. More study guide will be shared, what you need, and I'll give you time to prepare for that as well. So
Okay,
that, excuse, somebody ask a questions?
I was just saying thank you.
Oh, all right. Thank you. Appreciate it. So this is what we need to know here is that is how we go about with sulfur, sulfur difluoride, sulfur difluoride to fluorine molecular tetrahedral. So be careful when you answer the question, because a question could be, what is the electron domain geometry? Or what is the molecular geometry? What am I looking for? And that's why on my whiteboard, I gave you two answers based on how the question could be structured. Am I asking for the electron domain? It could be the same molecule, but here underline the word molecular geometry and know how to use that table. That table you see I've been referring to, it is posted on, this one is posted on Canvas. Please go download, print, practice with it so that you know how to use in the quiz and as well as in the final exam, So that is the rest of the molecular geometries, it follows the same trend. If you look at what is on the PowerPoint slide, right? I don't want you to just read and say, all right, tetrahedral, trigonal, pyramidal, and then expand. No, it will revolve around using that generic formula that how many lone pairs. Oh, yes, Jason, somebody was asking when will be our final exam. I said the final exam will be on the regular class time, 10:30 to, 10:50, not 10:30, because some people are working, some people, they have other agendas, and I don't want to schedule our final exam 4 p.m. yet you have another final exam 4 p.m. and so I'm assuming that you build your schedule, your work schedule, your other agendas throughout the semester around, and I don't want to change things around, all right? And then the quiz, I was saying that whatever I'm going through will not be in the exam, but will be in the quiz and final comprehensive. Having said that, for the remainder of the domain geometries, tetrahedral, octahedral, it is follows the same trend. Draw the Lewis structure. How many lone pairs are on the central atom, so that you describe what is given here as tetrahedral, octahedral, and tetrahedral. In this table here, this means you have 4 domains, 1, 2, 3, 4. And by the way, when you get to organic, not for us, this wedge, like it means going away from you, and this solid wedge coming towards us, and going back to something else. I don't want, just to give you an idea. So this has 4 domains. 3 plus 1 is 4, 2 plus 2 is 4 domains. And it has to do with what? A, P, 2, E, X, and so forth. That's how you use that table to predict the electron domain geometry. The catch here is, if you don't know how to draw the Lewis structure, if you make a mistake and omit some electron, for example, then you will make a wrong conclusion on what type of either electron domain geometry you expect to have. This one is tetrahedral from what I can see. It is silicon bonded to 2 chlorines. It doesn't really matter where you put, then hydrogen, and then hydrogen. Silicon is in group 4, and that's silicon oxide. So that's what I'll do for that. Please practice with those. You'll have that. I don't want to copy on this. We will start from this next time. So like I said, the midterm exam will cover up to 8.7. All right. I'll make quiz number 8 available, and please do complete the quiz. I'll make it due by Monday night so that when we meet on Tuesday, at least you'll have looked at. I will have made the answer key for the quiz available. You can use to study on Monday when we meet on Tuesday, or when you meet with the during the SI session. You can ask any question you may have before the exam on Tuesday. Other than that, by tomorrow, okay, by tomorrow, I will have the study guide available online that you need to read this, you need to read this, and you need to have this in the during the exam. Other than that, I want to stop here today. Thank you for joining in this morning. I'll see you again on Tuesday. We are almost at the last chapter for this course is chapter 10, which is fairly easy. It's on classes, and I know this is a topic you covered in introduction to chemistry. Other than that, the class is dismissed. If there is no more question, I will stop sharing my screen. Any question? Thank you. Have a good day. I'll see you again next Tuesday.